So in lecture 10, we will discuss mainly how we can construct latches or flip-flop by using logic gates. Okay, and also we'll discuss the difference between latch and flip-flop. Okay, we already discussed all these topics, the basic idea in lecture 1 itself. Now, after that, some of the characteristics of flip-flop called propagation delay, setup time, hold time, etc., and different parameters that we used in flip-flop. And after that, we will explain the operation of SR latch. Okay, and also the gated SR latch. What's the difference between a basic SR and a gated one? And also we will discuss gate level implementation of SR, JKD, etc. And finally, one important topic is a very important topic. It's known as a race around condition. It's actually a problem in JK flip-flop, and we will see what's the problem and how we can avoid this. Okay, so we'll start from the basic idea latch. We already discussed what do you mean by latch and flip-flop in lecture 1 itself. Now we'll discuss in a gate level how this different kind of latches are implemented. So latch or flip-flop means it's a bistable device. Means it's a device. Bistable means either the output can be 0 or it can be 1. So two stable state. Either it can continue in the state of 0 or it can continue in the state of 1. So that's why two states. That's why it's known as a bistable device, and which respond to the changes of the logic levels at the input. Okay, so we can apply input, and based on the input, the output Q or Q bar will change. Q and Q bar is simply the complement of Q bar is a complement of Q. So Q is the output and Q bar is a complement. So this is a valid case. Okay, and when the output of Q is high, we will call it the flip-flop output is set. And when the Q is low, we will call it as the flip-flop is in the reset stage. Set and reset. Okay. Now we can discuss how SR latch, okay, or RS latch. It's actually SR latch. Okay, how we can implement this SR latch by using NOR gate. We already discussed the truth table and all. Now we will discuss how we can implement SR latch by using NOR gate. So here you can see that this is a Q output and R input. Okay, R is indicated here, and corresponding outline is indicated as Q. When there is S and corresponding is indicated as Q bar. So please note down this. When you write S and S bar, first you write Q bar, then Q. So in order to avoid that, we are just replacing R and S. Okay. So normal way we will call it as SR latch or flip-flop, but in this case we are indicated as R and S only to represent Q at first. Okay. So now we need to analyze the working of this particular NOR gate circuit. Okay, NOR gate means if any one of the input is 1, output is 0. Okay, if any one of the input is 1, output is 0. That's the working of NOR gate in a simple manner. So here you can see that output of the first NOR gate is connected to the input of the second NOR gate. Okay, and similarly the output of the second NOR gate is connected to the input of the first NOR gate. Now we can analyze the working. For example, assume that both input R and S are 0, 0. So R is equal to 0 and S is equal to 0. And assume that the present state of the system is 0, Q is 0, so definitely Q bar is equal to 1. Now we can analyze. Okay, and if R is equal to 0, here you can say the Q bar is equal to 1. So one input is 1, another one is 0. So if any one of the input of the NOR gate is 1, output is 0. So the next state is also 0. Okay, and this 0 will be propagated to the lower side. Okay, if both inputs are 0, output of the NOR gate is 1. So we are getting exactly the same thing. Okay, NOR gate truth table. Now next we can assume that the initial state of this particular flip-flop or SR latch is Q is 1 and Q bar is equal to 0. So both input R and S are 0, 0. So we can analyze that Q bar is 0. So it is propagated to the input side of first NOR. Okay, this is the first NOR gate and this is the second NOR gate. And both inputs are 0 for the first NOR gate. So output is 1. Okay, it will maintain that state. And for the second NOR gate, the input is 1 and 0. So if any one of the input is 1, output is 0. So it will maintain the previous state. Okay, if it is 1, it will be 1. If it is 0, 0. So we can call it as it will maintain the states. So we will call this concept no change. Okay, there is no change in the state. Now we can verify the other input combinations. Okay, that is R is equal to 1. If R is equal to 1, R is equal to 1 and present state is 1. Okay, so if Q bar is equal to 0, here you can see that R input is 1 and one of the input of the first NOR gate is 0. So 1 0 means one of the input is 1, so output will change to, so this output will change to 0. Okay, so now 1 is changed to 0. Then this 0 is propagated to the second NOR gate input. So both inputs are 0 0. So this 0 will change to 1. Okay, 0 to 1. So here you can see that initially the present state is 1. Now that state is changing to 0. Okay. Now we can analyze one more case here. That is initial state of is 0. Okay. Q state is 0. Now we can analyze this particular state. If Q0, definitely Q bar is equal to 1. So Q bar is equal to 1. So the first OR gate inputs are 1 1. So definitely this output will be 0. Then 0 is propagated to the second OR gate input. So both inputs are 0. So output is 1. So if it is 0, it will continue like that, 0. So actually reset condition. If this reset means R is equal to 1, we will get reset condition that output is equal to 0. So we will call it as a reset condition. If you know the two table, we can verify that also. Okay. Now we need to consider the other possibility that RS inputs are 1, here it is 0. So S is equal to 1. So you can see that here Q is equal to 0. First case we can consider. Q is equal to 0 means second OR gate input is 0. So 0, 1. So definitely any one of the input is 1, output will change. So here Q bar is equal to 0. And if Q bar is equal to 0, it is propagated to the first NOR gate. And both inputs are 0, 0 means this 0 will change to 1. Okay. So you can see that output is equal to 1. Now we can consider other case. That is Q is equal to 1 and Q bar is equal to 0. Okay. And if Q bar is equal to 0, you can consider both inputs are 0. So output is 1. Okay, it will maintain that state. And Q is equal to 1 and S is equal to 1. So output will be 0. So it will maintain that particular state. Q is equal to 1 itself. So we can call it as a set state. Now the other two states, 1 1 are invalid in the case of SR flip-flop, because if you apply 1 1, okay, at this particular state, we cannot predict any output. So output is continuously changing. So there is no definite possibility for a valid output. For example, we can consider that case also. If it is 1 1 and assume that Q is equal to 0, Q bar is equal to 1. So based on that, if you observe the output cases, if both inputs are 1, for example, Q is equal to 0. If Q is equal to 0, you can see that it's 1 0. Okay, 1 0 means any one of the input is 1. This 1 will change to 0, and 0 will propagate to the first input. And if any one of input is 1, it's 0. Okay, here you can see that both Q and Q bar is equal to 0. So that is not a valid case. Q and Q bar are complement, but in this particular case, you are getting Q is equal to 0 and Q bar is equal to 0. So that's not a valid case. That's why in RS latch or in SR latch, we are not considering the last two statements. That is an invalid state. Okay. So we are not considering these two cases. Okay. Now we will discuss how we can implement a SR latch or RS latch by using a NAND gate. Okay. And here also you can see that a NAND gate is fed back. If you consider the first section, it's actually Q is fed back to the input of the, this is 1 and this is 2. Okay. And the output of the first NAND gate is connected to the input of the second NAND gate, and output of the second NAND gate is connected to the inputs of the first. But here it is indicated as S bar, and here it is R bar, because here we need to apply for a proper operation, you need to apply S bar here and R bar. So in order to get S bar, we will use one more NAND gate. Okay. So output of this particular NAND gate, if you apply S here, this is a NOT gate. If both the inputs are shorted, this NAND gate will operate as a NOT gate. So this is equivalent to NOT gate. So if you apply S, you will get S bar. And if you apply R here, you will get R bar. Okay. So this is working. We are going to apply 0 0. You can verify this 0 0. Both inputs are 0 0. And if both inputs are 0 0, you are here you will get 1 1. Okay. And Q is equal to 0, Q bar is equal to 1 is the initial state. And if Q is equal to 0, and here it is a NAND gate. In the case of NAND gate, if any one of the input is 0, output is equal to 1. So you can see that here Q is equal to 0, 0 and 1, so output is equal to 1. And if both inputs are 1, output is equal to 0. So we are getting exactly the same state. Now we can verify the other state. Now assume that the input is, output is 1 0 initially, and inputs are 0 0 means S bar is equal to 1, R bar is equal to 1. And here you can see that Q is equal to 1, so both inputs are 1, output is 0. And here one of the input is 0, so output is 1. So we are getting exactly the same thing. So now change. We are exactly getting the previous stage. Now we can analyze the other cases. Randomly, I will choose some cases. Let we can choose 1 0. Okay, let it be 1 0 state, and present state is 0. Okay, we can consider this particular combination. Okay. So if S is equal to 1, here we'll get 0, and R is equal to 0 means R bar is equal to 1. And the present state Q is equal to 0 here. So 0 here, and one of the input is 0. So the output is equal to 1. Sorry, here S is equal to 1 and R is equal to 0. And here you are getting R bar, S bar is equal to 0 and R bar is equal to 1. Okay. And assume that the present state is 0. Present state is 0. And here Q bar is equal to 1. And if Q bar is equal to 1, okay, if Q bar is equal to 1 and S is equal to 0, if any one of the input is 0, okay, output becomes 1. So this 0 will change to 1. Okay. Now this 1 is propagated input of the second NAND gate. So both inputs are 1 1. So output becomes 0. So now this 0 is changing to 1. And now we can verify another case. Okay. SR inputs are 1 0, so it becomes 0 1, and Q is 1. Assume that the next case, and here it is 0. Okay, in this particular case, Q bar is 0, so both inputs are 0 0, output is 1, and here it is 1, both inputs are 1, output is 0. So we will be seeing. So we'll get set condition. Now we can move to the other case, that is 1 0. So 1 0 we already discussed. Now we can consider 0 1. Okay, S is equal to 0, R is equal to 1 is a reset condition. So S bar is equal to 1, R is equal to 0. Assume that the initial state is 1, and here it is 0. Okay, and if If any one of the input is 0, output is equal to 1. So here one input is 1, another one is 0. So output of the second NAND gate will change to 1. Okay. So now this 1 is fed back to the input of NAND gate 1. So both inputs are 1. So this 1 will change to 0. Okay. Similarly, if you observe this, the other case, if you evaluate, you will get 0 here. Okay. And you can call it as a reset condition. And last stage is an invalid stage. So this is SR latch using NAND gate. Okay. In the case of NAND, please remember that we need to apply S bar and R bar. So in order to get S bar and S bar, we need to add an extra circuitry here. But in the case of NAND, if you are using R corresponds to Q. That's the difference you need to remember. Okay. Now we will discuss clocked SR flip-flop. In the previous case, we can see that whenever you apply an input, output will change. There is no control in the input side. Okay, whenever there are values of S and R changing, correspondingly Q and Q bar will change. In order to make a control over that input, we will apply a signal that is called a clock signal, or we can call it as enable signal. Okay, so this is an AND gate. For example, in the case of NAND, if one of the input is 1 and the other input is 0, okay, if one input is 0, irrespective of the other input, output is always 1. Okay, another possibility, if one input is 1, then definitely the output is equal to A bar. You will get the complement. Means here you are going to apply S at the one input, another input is clock. When the clock signal is equal to 1, okay, you will get S bar here. In all other cases, the output is 1, 1, 1. Okay. Here also, when the clock signal is 1, you will get R bar here. In all other cases, you will get 1. So by using this control, an extra control signal here, clock signal, we can disable the input side. Okay. Whenever you want to control this input signal, you can apply clock signal like this. So this particular enable signal is actually called clock. And here in the figure is actually indicated as a edge triggered clock. And generally, if you're not using any edge triggering, so here only we require a high signal, logic high signal. Okay. Whenever a high signal occurs, the output changes or input becomes sensitive. So we don't want to indicate any symbol here. Similarly, we can put a clock signal or we can call it as an enable. Okay. So this is the clock. Other workings are similar to the previous die. And other than this enable signal, we can add two more signals in the case of flip-flop or latch. Okay. And the basic difference, I can also say that when you compare a latch and flip-flop, okay, so this is latch and this is flip-flop. We already mentioned that latch is always level trigger, okay, and flip-flop is always edge trigger. Okay, so in between we will use both the names, flip-flop and latch, but basically latch means it's a level triggered one, and flip-flop means an edge triggered one. When the signal is high, the output will change, or input values are sensitive, then it is actually latch. So either you can call SR flip-flop or SR latch. Okay. So other two inputs that we are commonly used in flip-flop and latch, normally in flip-flop, they are known as asynchronous input. Okay, synchronous inputs means whenever you apply an input signal and the proper clock signal is applied, you will get an output. But in case of asynchronous, whenever you apply a signal at the same instant without looking into any clock signal, the output will change. So that inputs are known as asynchronous input. Normally, two types of asynchronous inputs are we are using. One is known as a preset, another one is a clear signal. There is no control over this asynchronous input. So whenever you apply preset signal or clear signal, the output will change. Normally, this preset and clear is active low signals. There can be active high, preset and clear also, but in most of the practical application, they are using preset and clear and active low inputs. So in as a general case, we will consider preset and clear in active low signal in the following explanation. So we will discuss what do you mean by preset and clear. Okay. Uh, at the output stage, okay, we will add an extra signal called preset or clear. Okay. Based on this particular signal, output can be disabled. For example, if preset is equal to 1 or the preset signal is equal to 0, that is, if any one of the signal is 0, okay, we are considering about preset bar. Means when it is 0, the signal becomes active. And this is an AND gate, and one of the input of the AND gate is 0 means output is 1. That is Q output is 1 irrespective of this particular clock, because clock has a control only at this particular stage. Okay. But the preset signal is applied at the final stage of the flip-flop. So when you apply a 0 through this PR signal, okay, the NAND gate, for example, this NAND gate 1, NAND gate output is equal to 1. Okay, output is 1 means Q output becomes 1. And we will consider another possibility, that is the clear signal is equal to 0. This, if the clear signal is equal to CR or clear signal, normally we'll write CLR bar, and here preset bar. Okay, if clear signal is equal to 0, one of the input of the NAND gate of second NAND gate is 0, so output is equal to 1. If Q bar is equal to 1 means Q will be definitely 0. Okay, it's a flip flop. And so this is the working of clear and preset input. Okay, forcefully you can make the output is equal to 1 or 0. In order to make Q is equal to 1, put preset signal is equal to 0, and in order to make Q is equal to 0, make a clear signal is equal to 0. Okay, now we can see the truth table of SR flip flop with preset and clear signal. Okay, if both clear and preset signals are high, it's an invalid case because it's an active low signal. So 1 1 1 1 1 1. The first 4 cases shows the normal operation of flip flop. So when you apply clock signal, okay, let it be 1 1 1, the clock signal, it will operate as a normal SR flip flop. 0 0 output is Q, so it will be C Q. Okay, so Q bar itself. And here it is, if it is 0 1, a reset condition. Okay, if it is a reset condition, Q will be 0. Okay, if it is set condition, Q will be 1. And here 1 1 is an invalid condition, so we don't want to bother about it. But if the clear signal is equal to 0, see in this particular table, clear signal is equal to 0 and preset is equal to 1. And irrespective of whether the clock is high or low, that is indicated as a dot care condition. Okay, Q becomes 0. Okay, that is the working of clear signal. When clear signal is equal to 0, Q is equal to 0. That's a clear. And when preset signal is equal to 0 and clear is equal to 1, Q output is equal to 1. Okay, and if both signals are 0, again it's an invalid case, so we don't predict what will be the output. If any one of the signal is active, we can say the output will be 0 or 1. If clear is equal to 0, output will be 0. If preset is equal to 0, output is equal to 1. Okay, that's about it. The exactly the same thing is mentioned here. Okay, both 0 0 or both 1 1, we cannot predict the output. Now we'll discuss the D flip flop as a slightly modified version of SR flip flop. Okay, we already discussed a flip flop conversion SR to D flip flop. So here you can see in SR to D flip flop, the SR flip flop, this S and R. If you connect a NOT gate, you can simply implement a D flip flop. Okay, from SR. So all other working are same. So here you can see the clock signal. It's a gated one. Clock SR flip flop. This shaded portion is actually indicating SR flip flop. Slightly to modify this D flip flop, we will connect a D input directly to S, and this is a NOT gate. So D bar will be applied at this particular input. For example, if it is 0, S input will be 0 and R input will be 1, and it will operate as 0 1. 0 1 means it's a reset condition. R is equal to 1. If R is equal to 1, Q will definitely 0. Okay, and the other case, that is if D is equal to 1, S is equal to 1, and R is equal to 0. So in this particular case, it's a set condition, so definitely Q will be equal to 1. Okay. And all other working are the feedback condition, all we can explain from the previous knowledge. Okay, this is a D flip-flop. Now, similarly, you can implement JK flip-flop from, if you know the concept of flip-flop conversion. So this is SR, and we can convert this JK by simply connecting the Q bar is J and the K input. So this is a simple flip-flop conversion technique used in SR to JK. Okay, if you know this, you can simply modify. You can watch, I think, lecture 6 or something. There is a, I think, lecture 6 or 4. You can watch for this flip-flop conversion. And if you slightly modify this, you can see the Q bar is connected to the input side through this J input, and Q output is connected to the K input through the clock. Okay, there's a slight modification. So SR flip-flop can be slightly modified, and it will operate as a JK flip-flop. Okay, so all other working are similar. Okay, only thing we are taking the inputs Q bar and Q in this particular case. Okay, so this is a working of JK flip flop, and if in the case of JK, if both inputs 0 0, output will be QN, and if it is 0 1, it's like SR. Okay, if R is equal to 1 or K is equal to 1, it's a reset condition. Okay, if S is equal to 1, it's a set condition, and 1 1 means it's a toggle condition. So we will get just opposite of the previous case. So very important, when it is 1 1, in the case of SR, this particular case invalid, but in the case of JK, you will get the toggle mode. Okay. In the previous case, you can see that the JK implementation using NAND. Similarly, in the case here, you can see JK input, JK flip-flop by using NOR gate. Okay, so this is an OR gate or RS latch. RS latch can be modified as a JK. Okay, here you can see JK. All other working are similar to that. If you know the SR, you can explain any JK, any flip-flop. So now we will discuss another concept which is known as the edge triggering method. Okay, in the previous examples, we discussed the level trigger because the flip-flop or latch will be enabled only in the positive duration. Okay, now we will discuss either rising edge or falling edge sensitive. That's edge triggered flip-flop. So in order to detect this pulse transition, we are using an additional circuitry. Here you can see how we can achieve that particular. It's actually a latch. This is bubbled. OR means it's actually NAND. Okay, so this is a NAND gate implementation, exactly same as SR using NAND. So instead of enable clock, we are using a edge triggered clock. So we are applying the clock signal here. So this is a clock signal. So here you can apply the clock signal, and here you can see a NOT gate. And we know that when the signal passes through the gate, there is a propagation delay. And the lower path you can see is directly connected by a wire. In the case of wire, there is no delay. But in the case of when the signal passes through the gate, there is a delay. So here you can see a NOT gate. So you can draw the waveform like this. Okay. This is the original clock signal. So this is a clock signal we are applying. And we know that this is a NOT gate. So when the signal passes through the NOT gate, so we are expecting an output from 0 instant, but there is a small propagation delay. So output will change only after some duration. But there is a wire actually. In the case of wire, there is no propagation delay. So exactly the clock signal you will get at the same time. So the input of the NAND gate will be like this. So this will be, for example, this is 1 and this is 2. So this is one input and this is another input. If you consider this NAND gate output, see for this particular duration, okay, the signal value is 1 here, and here also the signal value is equal to 1. So both inputs are 1 means output is equal to 0. Okay, for this duration, output is equal to 0. And after that, one input is 0, other input is 1. So output becomes high. Okay, this will be the case. Before that also the output is high. For a small duration, Actually, we are applying a long pulse, positive going pulse, high signal, but this signal is actually reduced to a small narrow pulse, which is a low pulse. Okay, and if you use a NOT gate, this becomes active high signal. Okay, so the long pulse is now reduced to a small signal, and it will be high for only for a small duration. Okay, and this small pulse we can consider as a positive edge triggered signal. Okay, so here you can see that this small duration signal again complemented by using a NOT gate. So this is simply a small pulse. So the entire circuit input will be active only for a small duration. Okay, for a small duration, input will be active. Okay, in the previous case, the input is active for a long duration. If you are using this clock signal directly, it will be active for this much duration. And now we are discussing how we can reduce that duration. Okay, so the input will be sensitive only for a small duration. So definitely it will act as a positive edge triggered clock. Now we'll discuss one of the main problem that occurs in the case of a JK flip-flop. Okay, we know that, and this problem occurs in a JK flip-flop level triggered one. Okay, not in edge triggered, and level triggered one. We know that when both input J is equal to 1, K is equal to 1, it's in the toggle mode. Okay, toggle mode means the Q output will change to Q bar. Okay, for example, assume that both inputs are 1, 1, and we are applying a clock signal which is high from this particular instant, it is high. Okay, this is the time 0. T is equal to 0 onwards, the signal is high. And assume that the present input is 0, here it is 1. Okay, and JK inputs are 1. And we know that it's a level triggered one, input is active. So initial state is changing and it is 0, 1. Now we can see that Q bar is fed back to the input side. Okay, Q bar is fed back to the, sorry, Q is fed back to here. So here it is 0, and this one is fed back to this point. Okay, if this is the condition, again there is a change. So JK inputs are 1, 1. Again there is a change in the output state because the clock signal is again high. So what happens is that the output again changes to 1, 0. Okay, assume that the time reaches at this particular point, T1. Again assume that the clock is high and JK inputs are high. Again what happens, this input is fed back to the, output is fed back to the input side. So again there is a change. So this 1 will change to 0, 0 change to 1. Okay, so okay, now I can explain the same thing by using this particular waveform. Here you can see the clock signal is high from this particular point. Okay, and JK inputs are 1, 1. Okay, at this particular instant. So I already mentioned that when the JK inputs are 1, 1 and the clock signal is high, output will be toggle. So initially output is 1, so now it is changing to 0. Again, during this particular duration, the clock signal is high, so 1, 1 input, so output will change. So there is a sudden change of 1 to 0, 0 to 1 occurs for a particular condition. When the clock signal is high, and one more point, remember that this particular JK flip-flop is a level triggered one, and JK inputs are 1. So you can see that Q output is continuously changing. This problem is actually known as a race around condition. Okay, and this race around condition occurs in the case of JK flip-flop and in the case level triggered JK flip-flop. And we need to avoid this particular unwanted case. So in order to avoid this case, we can use either a edge triggered JK flip-flop or master slave JK flip-flop. So already we discussed what you mean by an edge triggered. So reduce the duration of the high level and make the flip-flop work in a small duration pulse. Okay, either in positive edge triggered or in negative edge triggered. Another solution is known as the master slave JK flip-flop concept. This concept is actually very important. Okay, here you can see the master slave concept. So the first section is actually exactly similar to your previous case, but only one difference: the output is not fed back to the input side. Okay, this is one JK flip-flop. In this particular JK flip-flop, the output is not fed back to the input side. We will use one more JK flip-flop here. Okay, and output of the second JK flip-flop is connected to the input side of the first one. So this is stage one actually, and this is stage two. Okay, stage two output is fed back to the input side. So this is the master slave arrangement. Okay, and the first JK flip-flop arrangement is known as a master, and second one is known as a slave. And you can note down one important point here. The first flip-flop is operating, JK flip-flop is operating on the positive edge triggered clock, okay, or level trigger. You can consider as a high. And this clock signal is complemented here by using a NOT gate. And the second slave latch or slave JK flip-flop is actually working in the negative cycle. Okay, so when you apply a clock pulse, the first latch will operate during the high. When it is high here, the first latch will be active. You will get a definite Q and Q bar here. For example, it can be A and B. Okay. Now you can see that at that particular instant, for example, there is a Q and Q bar. In the first high duration, the first master flip-flop will be active and you will get a output, let it be A and B. And during that duration, this slave will be in disabled mode because the clock is inverted. So here we will get active low signal. So the slave latch will be in disabled mode. The previous value of Q and Q bar will be maintained. Okay. So previous value Q and Q bar will be maintained. And the JK flip-flop input, now we are moving to the negative half cycle. So when you apply the negative half cycle, so it becomes 0, and here is a NOT gate, so this becomes high. And we can say that the first becomes disabled and this becomes active. Okay. So this already latched value A and B will be fed into this particular slave latch, and corresponding output you will get at the output side. Okay. So in this case also the output is fed back to the input side, but in this particular instant the first latch or master latch is in the disabled one, because the master will operate in high and slave will active only in the low state. At a time any one of the circuit will be active. So the continuously changing problem can be avoided by using a master slave arrangement. So the reserve condition problem occurs only in a level triggered. So we'll make an arrangement called master slave. First master flip-flop, another one is a slave flip-flop. And at a time, any one of the circuit will be active, either master or slave. Okay. So masters normally operating in a positive level, and the slave is normally operating in a negative level or low level. Okay. So by using this particular configuration, we can avoid this race around condition. So now we will discuss some characteristics of flip-flop. One important characteristic is known as the propagation delay time. Okay. So in the case of gate or flip-flop, okay, when you apply the input, at the same instant, we will not get the output. Okay. When it processes to the flip-flop, so there is a small delay. For example, if it is a D flip-flop, you can see the applied input will reflect the output side only after a particular time. For example, we are applying a low to high signal at the input side, and the Q output we are obtaining. Or you can assume that the clock signal. We applied a clock signal and we got the output change only after a particular time. And this duration, low to high transition, is normally called TPLH. And it will measured from the 50% point on the triggering edge of the clock to the 50% point on the low to high transition of Q. So this is known as TPLH. And similarly, there is a high to low transition. And this high to low transition we will call it as TPHL. These are the two propagation delay that we need to expect in the case of flip-flops. Normally, these values are provided by the manufacturer in the data sheet. Another important time is the setup time. Okay, setup time is actually indicating the minimum time we need to maintain the input constantly. For example, we will normally will say that when you apply the clock signal at the same instant, the input will be sensitive. But in the practical case, that's not valid. So before applying the clock signal, so this is the instant where we are applying the clock signal. Before applying the clock signal, we need to maintain that input for a small duration. And the minimum duration for which the input should be maintained is known as a setup time. Okay. And if you are suddenly changing the input at this particular instant, it will not be detected. Okay. So before applying the clock signal, the input should be maintained for a small duration, and that duration is known as a setup time. And similarly, after applying the clock signal, so this is a clock signal. We already mentioned that before applying the clock signal, we should maintain this input for a small duration, that is the setup time. And similarly, after applying the clock signal, suddenly we cannot make it zero, or we cannot change that value. We need to maintain this value for a small duration, and that duration is actually known as TH, hold time. Okay. So in the case of flip flop, we need to maintain the input for a small duration, TS plus TH duration. Okay. So with respect to the clock signal, so that is a hold time. And the maximum clock frequency based on the previous parameters, propagation delay and setup time, hold time. Okay, if you consider all these factors, there is a maximum clock frequency for the working of flip flop. Highest rate at which flip flop can be reliably triggered. Okay, this value is also provided by the manufacturer based on the propagation delay and other delays considered. So the maximum clock frequency is also one important parameter in the case of flip flop. Okay, if you are giving clock frequency higher than this, flip flop will not work properly. Another one is a pulse width. Even if you are using a clock signal, okay, sometimes you will apply a clock like this, but it's not a valid case. In the case of flip flop, the on time and the off time, or logic high and logic zero of the clock signal should be maintained for a particular duration. This duration is also specified in the case of manufacturer will provide that details also. So, and this details also for the clock and preset and clear. And what should be the duration? We should maintain the signal for high, and for the clear and preset signal, when you draw the waveform, we will simply draw a active loss signal, for example, clear signal. But this duration is usually specified by the manufacturer. So for that, you need to verify the data sheet. Okay. Last point we need to discuss is about the power dissipation. Okay, if you consider any flip flop, so we'll apply a plus 5 volt for the working, and for the working it will also use consume some current. Okay, for example, consume 5 milliampere current. So the power consumption of this particular flip flop, you can consider VCC into ICC, which is 5 into, in this particular example, if the input voltage is 5, DC power supply is 5 volt, and the current consumed is 5 milliampere, you can say it's 25 milliwatt. And if you are operating more number of flip flops in the same IC, it will consume more current, but voltage will be same. Okay, assume that if a single IC contains 2 flip flop and the power supply used is 5, but the first flip flop is alone working, it will consume 5 milliampere. If the second flip flop is also working, again a 5 milliampere, so total current becomes 10 milliampere. Okay. This is all about gate, how we can construct flip flop using gate and the characteristics.